So chapter 6 was more applications, but the integration was quite simple. The integration was just the very basic integrals because you only really knew U substitution and the basic like power rule and stuff like that. Chapter 7, while the integration, the actual calculus piece is going to be harder, we're not really applying it today. We're literally just going to be doing integrals. So you're going to take an integral and do it. You're not going to have to try to find the integral and stuff like that like you had to do for the volume and stuff like that. So it's one less step you're going to have to do. The integration is just going to get a little harder. The nice thing is, though, we'll practice the integration. We'll also practice a lot more of the differentiation because when we're looking at today, when we're doing integration by parts, we have to do both. So you're going to be able to get practice on those things as well. All right, so every rule that we did for a derivative, we have to have basically the inverse rule for integration because integration undoes it. So the chain rule was the differentiation, and then we had U substitution, which was the integration part of it. The rule we're going to look at tonight is the inverse for the product rule for derivatives, and that is known as integration by parts. So let's quickly look over remember what the integration or the derivative rule was for the product rule. So the derivative stated that if you're doing the product of two things, you take, and I always did it, the derivative of the first times the second, then the derivative of the second times the first. So I actually reversed these just because when we do the subtraction or the quotient rule, it kind of made a little more sense. So it was f prime of x times g of x plus f of x times g prime of x. Since it's addition, it doesn't matter. We can do it in either order. It doesn't make a difference. So the question is how would I go from this back to f of x times g of x? Because that's what we'd actually want to do. We want to be able to undo the product rule. And that's integration by parts. So I'm gonna literally go through and show you how it's done, and then we're gonna do problems with it. So if you don't get this part, don't freak out too much. When we start to do it, I think it makes a little more sense. Except sometimes it's good to know like the theory behind it, like how it actually proved out. So I tend to do both. So remember, if I take the integral of a derivative, it cancels itself out. So if we did the integral of both sides, which is what they did here. So they took the integral of, so that right there is my product rule. And then the integral of that basically came out to be just the f of x times g of x. Remember that we can split up the integral. We can have the plus, we can split it up into two integrations. So that's all they did there. And then they decided to move one of them over. And it doesn't make a difference which one you move over. So they decided to move that one over. So we've got this. So what we have now, crazy as it is, with just a few little steps, we have now the integral of a product. We have the integral of f of x times the derivative of g of x. And what it equals. F of x times g of x minus the integral of g of x times f prime of x. The key is finding all those pieces. So what we're going to use is this formula. So remember, calculus has two main people that created it, Newton and Leibniz. Newton or Lagrange, who kind of formalized Newton's methods, does the f of x, g prime of x. That's their notation. Where Leibniz did u's and v's and the dx, dy's, and those things. So I like Leibniz's notation better for this. It's simpler to look at. So my integral is u dv. That's what I'm multiplying by. So I'm going to always be given in every problem a u and a dv. What I need to find is I need to find the du and I need to find the v. So we're going to be given these two, and we need to find those two. Okay? So every problem that we do, we're going to set up in that method. We're going to have u du, v dv, and we're going to plug things in and find those pieces. And then it's just plug and play. We got to plug it right back into the formula and get my answer out of it. And the formula is uv minus the integral of v du. So that's what I'm going to plug it back into. All right, done with the lecture. Now let's actually do some problems. Hello. All right, so let's look at this one. We have the integral of x times sine of x. So first thing is, this is a product. So I've got to use integration by parts. So I've got u du and v dv. Hold on a second. My doggy's got into a fight, so just trying to get him out of the crate. All right. So yeah, sure. The most important part that we're going to do is we need to figure out what piece is u and what piece is dv. So if we're looking at it, this part right here, this integral piece over here, I got to make something there that's going to be easy for me to do. At least easier than what I started with. Yeah. Du. Sorry. Yeah, I got to make my u's a little less pointed. Yes, that's du. So my goal is to make that piece as easy as possible for me to solve. Otherwise, I didn't make my life any easier. So when we're picking things, I basically want to make that part right there simple as I can. So I got a choice between x and sine of x. If I put x here and I do the derivative of x, what do I get? What's the derivative of x? Because du is derivative. So what is it? 1. So that's just 1 dx. Is that simpler? Yeah. Let's say I made it sine of x. If I did the derivative of sine of x, what would it give me? Cosine of x. Not really much simpler. Right? Because I'm still going to have that trig function there that I'm going to have to deal with. So we want to pick, in this case, we're going to make u my x. That means my dv is sine of x dx.
So for you just pick the easiest.
You're not necessarily picking the easiest derivative because the derivative of sine is not that difficult. It's the derivative that's going to get rid of something. because and on the next slide I'm going to show you, I'm going to give you a method to do it. But the goal is to get something that simplifies the problem, because even if I have to do another step, I want it to get simpler every time I do it. So going from sine to cosine doesn't really make my problem any simpler. I'm still going to have a multiplication step there, which means I'm going to have to do it again. Where going from x to 1 eliminates one of my pieces. So that makes my life a little simpler. And that's the goal. All right, so if this way is derivative, going this way would be my what? Integration. So what's the integral of sine of x? Negative cosine of x. So your first step when you're looking at this is you have to figure out what u is and what du is, or dv. So u and dv. And then you're going to find the other two pieces. To find du, you do the derivative. To find the v, you do the integral. So I said, we're going to practice our derivatives here. All right, so this was my integral. So now let's plug in my pieces. So u is x. V is negative cosine of x. Minus the integral. V is negative cosine of x. And du is dx. So I have negative x cosine of x. Now what's the integral of negative cosine of x? Negative sine of x. Because going up, sine, cosine, negative cosine. So negative cosine goes to negative sine. So it's negative minus negative sine of x plus c. So I get negative x cosine of x plus sine of x plus c. And that's my answer. Now, yeah.
Second part is the rising integral sine is the BDU.
Yep.
So what happens to the value of u?
It was 1 dx.
So you just there.
I didn't have to put the 1.
Oh, okay.
Yeah, that was the only thing. I didn't have to put the 1. If you put the 1, it's fine. Because 1 times anything is just whatever's there. So it wouldn't have changed the problem. If there was something there, you would have had to put it. And we will definitely see that in a couple problems from now. So they won't always be 1. All right. Any questions on the steps in the process? All right. This, it's kind of funny. So you would think a book would put like this information in the actual book. No, this was in the answer guide. So this is just a mnemonic, just like PEMDAS and stuff like that. I'm going to rewrite it out. Don't worry. I know it's kind of really tight. And actually, the only thing you really need is, let's see if I can make this a little bigger. Actually, the only thing you need is that. So when you're choosing what thing to set for your U, this is what you want to go by. So you want to do logarithms first. And inverse trig functions, so arc sine, arc cosine, those things. Any algebraic, that's just your x's. That's your x squareds, x's, the polynomials, those types of things. Then trigonometric, then exponential. Think about it. If I do, what's the derivative of e to the x? Right, doesn't solve anything, right? It's not going to change anything. So you basically never want to set that as u. Unless you have no other options, you basically have two of them. Because it's not going to help you. It's not going to make the problem any simpler. So this is the order you want to do them. So when you're looking at having multiple things, start at the top and work your way down. That's how you pick your u. And then obviously the other thing is always your EV. So it's logarithm, your inverse trigonometric, which is not cosine, I'm not cosine, cosecant, secant, it's the arc sine, arc cosine, arc tangent, those. Algebraic, trigonometric, and exponential.
So that's the mnemonic for choosing u.
That's the mnemonic for choosing u, yes. And then whatever's left over will be your dv. All right, everybody got this down? Because out of everything, this is probably, other than the actual equation, this is probably the most important piece. All right. Break this. I didn't do another one before this one. Hold on a second. I might do another one before that one. Yeah. Okay. All right. What's the integral of ln of x? No. The derivative, the integral of 1 over x is ln of x. Huh?
Wait, you said derivative?
Oh, I meant integral. Sorry, you might have said derivative. So the integral of the integral of 1 over x is ln of x. So the derivative of 1 over x is ln of x. No, the derivative of ln of x is 1 over x. So what's the integral of ln of x? No, integral. I said integral this time. So what's the integral of ln of x? Huh? We're going to. So one of the things that derivatives, the advantage derivatives have is there's actually rules that you have, and then pretty much everything you can come up with those from those rules, and it's pretty simple. If you look in the back of your calc book, they got like 1 page of derivatives. The integrals, there's like 190 different rules. Most of them you actually can figure out from the steps. The problem is it just takes a long time to do it sometimes. So for example, this one, the integral of ln of x, it seems very, very simple to do. The problem is we don't know what it is. It actually has to be done by integration by parts. So what we're going to do is, remember in the last problem, you asked a very important question, what happened to the 1? Well, and I said I didn't have to write it, right? I didn't. However, I can. So I have udv. So if we look at my mnemonic, what's the very first one? Logarithm. Logarithmic is first. It's before even the algebraic, which is everything that you would normally think of. Okay? So I'm going to set my u to be ln of x and my dv to be 1 dx. All right. Now, what is the derivative of ln of x? 1 over x. That's 1 over x dx. What is the integral of 1 dx? That's just x. Okay. So now, let's plug in our information. So remember, we have it's uv minus the integral of v du. So u is ln of x. V is x minus the integral of v is x. And du is 1 over x dx. So this is just x ln of x. Now this part over here, that's just the integral of 1 dx. Because the x and the ln of x cancel each other out. So what's the derivative of 1? I mean, the integral of 1 is x plus c. And that's the integral of ln of x. So you can start to see how really everything comes from that. Get that right, plugging in stuff, solving the rest of it's pretty easy. Got to get that right, though. All right. So I want you to find me these 4 things for this problem. It's the integral of x squared e to the x dx. All right, so which one did you set for you? X squared. And then dv would be my ex dx. Okay. So what's the du? Almost. Don't forget the dx. It's important. And what's v?
Yeah.
It's just e to the x. Okay. Plug it in. All right. So what's the integral of e to the x 2x? We have to do it again. We still have a multiplication. So the question, though, is what we have there simpler than what I started with? Or did we make a mistake? So we went from an x squared to an x, right? If I did it again, the x should disappear. So it's getting simpler. And actually, so in my Calc class, like 4 or 5 years ago, when I taught Calc 2, so for those of you who had before, you remember, so basically I make a review sheet and then I make an actual test. They're basically the same. I just changed some numbers. Well, I wasn't thinking when I changed some numbers. I just randomly changed the number. I did it on this problem. And I changed it from x squared to x to the 5th. Not thinking, just changed one number. The problem is now you have to basically do this problem 5 times to get rid of it. And I'm like, they were starting to why is it taking so long? I'm like, oh crap. So you can start to see how that's why the algebra one, while it's technically simpler to do, logarithms and inverse trig functions actually break down faster than algebraic ones do, unless it's really close to being just a variable. So we have to do this one again. So I have u du and v dv. So I'm going to do the same process. I'm going to make my u 2x and my dv e to the x dx. So v is e to the x dx and du is 2 dx. So I have my x squared e to the x minus, so we still have that out in front. There was a reason I was using different colors. Now I have 2x e to the x minus the integral of e to the x 2 dx. So I've got x squared e to the x minus 2x e to the x. What's the integral of 2e to the x, basically. It's just 2e to the x, right? Plus c. Since these are indefinite integrals, you have to have the plus c. Is the process making sense? Huh? Yeah, that's what I said. It's as long as you get one of them, you're good. It's like as long as you can do it. If you don't understand exactly where it came from, that's fine. As long as you can do it. So as long as the process that we're going through makes sense, you're fine.
So I do have a question.
Yeah.
How come it's not 2x for 2ax? Wait, how come it's just 2?
Because it's 2 times e to the x. It's not 2 plus it.
Oh.
If it was plus, then yes, it would become 2x. But since it's multiplication, it's a coefficient. Good question. See, told you other people have the exact same question. So that's the thing. It's like when you're looking at it, those are the little things that can mess you up. Mixing up your derivatives and integration can mix you up quite a bit, especially when you're looking at the derivative of a constant is gone. The derivative of an integral, a constant, or the integral of a constant becomes 2x. That can make a difference when you're doing your problems. So just be careful with those. Sines and cosines, that one kind of reverses itself. So same concept, looking for your sine. We had to go twice because we have this piece right here. It's still an integral, and it's still a product. So there's no easy way to do that integral without doing integration by parts again. So that's why we had to do it twice. All right. All right. Find me the integral of this. What did you set as your U? Okay. I had to pick 2x. kind of gets rid of it, which is nice. Okay, so that means my dv is the square root of 1 plus x squared. I gotta do the integral of that.
Change the square root to 1 over 3 by that.
Okay, so I just got this. How do I find the integral of that?
I got is 2 words times 1 plus x power.
Okay. So you started doing the chain rule, but didn't finish it. I'm sorry, you started doing U substitution, where it kind of like the reverse of the chain rule, but didn't finish it. So if we're looking at, if it's the derivative, that'd be fine. You do the derivative of the inside multiplied by that. If we're doing the integration, we have to do U substitution. So if I say, bless you, this is if you're done now. If I make m that, so then dm is going to be 2x dx, right? Because I can't use u because I already have u up here. So, and then u or m to the 1/2 I could do. The problem is I kind of need a 2x dx. Look at your original problem. Do I have a 2x in that problem? Yes. So here's your first lesson when you're doing integration. The most important thing ever. Don't always look for the hardest way to do a problem. Okay? The first thing you look at in integration is, can I just do the integral without doing anything? Look at it. All right? Second thing, can I do substitution? If you can't do those, then start looking at the harder ones to do. This one, I didn't need to do the integration by parts. I can do substitution with it, which is a really simple way to do this problem. Okay? So don't automatically assume, even if it's in the same section, that that's the method you have to use to solve the problem. Look for the simplest way to solve a problem. All right? So in this one, I'm going to set u to be 1 plus x squared. So du is 2x dx. So now my integral that I have is u to the 1/2, because that and that cancel out and become just du. So the integral of this is 3/2. So it's over 3. So this answer ends up being 2/3 1 plus x squared to the 3/2 plus c. Sometimes the simple ways work. Okay. I know it was a tricky little problem I threw in there on purpose, but it really means something. It's like don't automatically, it's like look at things. It's like look at what you got, look at what they're giving you. U substitution's a heck of a lot easier than integration by parts. And trust me, U substitution's like light years easier than partial fractions, which we're going to have to do in next week. So it's like the process doesn't get easier, it gets harder, because the easier things don't work. All right, so we have to come up with another process to be able to solve those situations where the easy things that I've already come up with don't work. But always start off with the easy ways. All right, this one. I promise you this one you have to do integration by parts. So set this one up for me. All right, which one's my U? Yes.
Either can be simplified.
Yes, but it does actually matter. Nope. Trigs before exponential. So the sine of x is my U.
You
And
say exponential, is that just anything?
e to the x, anything to the x power.
Okay.
E to the x, 2 to the x, 3 to the x, 4 to the x, anything. Not just the e. All right, so my du is x, and my v is e to the x. All right, so it's u. Actually, I'm going to put the v first just because I want the e to the x in front. Minus e to the x cosine x dx. All right, so we're here. Okay, so we now have to do the integral of e to the x cosine x, right? All right. So we have to do basically integration by parts again, right? So we're going to do the integral of this piece right there. So again, I have u du and v dv. So my u is going to be cosine x, and my dv will be ex dx. So my v is e to the x. What's my du? Minus sine x dx. All right, so we've got and then we've got e to the x cosine x minus the integral of e to the x negative sine x dx. Can I pull out that negative sign? Yeah. So those are going to become basically, those will both be positive right there. All right, so if I clean this up a little bit, I have e to the x sine x minus e to the x cosine x minus the integral of e to the x sine x dx. All right, what do I gotta do now? Ah, very good. Yes, it seems to have looped. Yeah, which is what I'm gonna do right now. So it seems to have looped, right? This right here is the same thing as the beginning. If you notice, this is the very first problem that I've done, and probably should have done this all along, but I rarely you have to. That I actually wrote the exact problem as I was going through and doing it. There's a reason for that. Because you can work on both sides of the equation. So I have this. I can add this to this side here. So I'm left with 2 integral e to the x sine x dx equals e to the x sine x minus e to the x cosine x. Ooh, that's horrible.
Yeah.
I was like, ooh, that's horrible. All right, let's not use blue. Yeah, I knew yellow was bad. That's why I didn't go to yellow. All right, we'll just stick with the black. The red seems to be okay, though. Yeah, unfortunately, I don't have that option here. So I have 2 integral e to the x sine x dx equals e to the x sine x minus e to the x cosine x. So I basically, whenever you see a problem that's starting to loop that goes back to what it originally had, you can do this. And now I'm just going to divide the whole problem by 2. So the original problem was the integral of e to the x sine x dx. So it equals e to the x over, actually, I'm not going to do that too, because I know somebody's going to ask me, where the heck did that all come from? All over 2. I was going to write e to the x divided by 2 and then write the other thing afterwards. Plus. Yeah, plus 2. I forgot the plus 3. So that's the answer. So that's how you deal with the loop. And it did make a difference if I didn't, because the sine and the cosine is a loop. E to the x doesn't. And I needed it.
Loops faster, I guess.
Yeah, it doesn't loop at all. So it's like I needed that to change a couple times to be able to go back to it. So that's what we got.
What can you do with this?
Nothing. Okay. So, in all honesty, the things that you're going to do with this is you're going to apply it in other classes, in other situations. So, actually, I can pull up some problems for you, just because trying to make these up off the top of my head is just never going to actually end up happening. Since I know there's a bunch of you in here that are engineering and physics type majors. This is looking at hydrostatic pressure and force on a dam. So that's the dam, that's the water. We want to look at the pressure at certain spots. When you go through and do all the wonderful math and everything else, you get a crazy integral at the end that you have to deal with. Okay. So you're not necessarily going to do just the integral. You're going to be given a situation that you're going to need to find information for, that you're going to have to use integration to find it. That's where you use it. Now, I will honestly say the vast majority of you will never do this by hand. You're going to plug it into a computer and have the computer do the integration for you. because you don't want to make a stupid little mistake that's going to cost somebody millions of dollars. But that being said, you also want to have a general idea of what the answer should look like, so that if you screw up and move a decimal point by accident in your problem, you know that the answer doesn't make sense. And that's important. Remember the Hubble Space Telescope? It was actually the lens for the Hubble Space Telescope was created in Danbury, Connecticut. Yeah, the scientist who did it screwed up by a decimal point. He was off by less than the thickness of a human hair in his calculations. He was always by 1 decimal point. It was like a million, like 6 decimal places after. It was off by a tiny little bit. However, that tiny little bit that he was off on the lens caused all the pictures to come back from the Hubble Space Telescope as blurry after it went up into space. Now, every one of you have seen pictures from the Hubble Space Telescope. It's no longer blurry. They had to send another $700 million space mission up to put glasses, in essence, on the Hubble Space Telescope. They had to put a corrective lens to fix that little mistake. And it cost us $700 million. Okay? So that's what I'm saying. Little tiny errors can cost millions, depending on what you do. If you're working at EB, a little mistake could sink the sun. That's why we have millions. That's why we have like multiple people checking the math and everything else. All right. So it's not necessarily that you're ever going to do a problem just like this, but problems like this are used actually in engineering and physics and biology and probability and statistics and everything else like that. That was just one example. If you look at, we're going to actually do some of the stuff in chapter 8, and so let me ask this question because I'm going to have to plan for this, and I really hate that section, but that's okay. How many of you guys are actually physics and engineering majors? How many of you guys are like economics, biology, like human, like that type of stuff? Just one. Okay. Then I'll do the engineering section, as much as I don't like that section. I typically do the probability and stats section just because it's math and I know it. I'll do the engineering section because it at least the stuff, it's chapter 8 because it uses all the integration, that stuff that you learn in chapter 7. Just like the chapter 6 stuff was just the rotations and stuff, it was using the integration that you did in chapter 5 to apply it. That uses it to actually do the applications to real world situations of this stuff. So I will do the engineering section, which means I need to study. I know the math. I don't know how to apply it very well because I've never had to. So, but I will figure it out so I can teach it to you. All right. So that's why. All right. Let's do. Yeah, let's do this one, and then I'll give you guys a couple to work on. Yes, this is a definite goal because I want to do at least one definite goal. Okay. All right, so think back to what we had to do with that LN problem. There's only one piece in this problem, right? It's just the tangent -1, the arctangent of x. So we're going to have to set this up as a 1 dx type situation. So the question is, where do I want to put my arctangent? As that's u, because the inverse tangent function or the inverse trig functions were before the algebra functions. So that's tan -1 of x. And then this would be just dx. So the integral, that would be x. Nice and simple. Now, what's the derivative of the arctangent of x? Almost.
Like,
You're in the right
like,
range.
like,
Yes, you're in the right range. That's actually sine. The tangent one is the one that doesn't have the square root. It's just 1 plus x squared. So it's 1 over 1 plus x squared dx.
How do you recommend we remember? Like,
You don't. You don't.
Like
I
for the exam,
I didn't remember it. I looked it up. You get an index card for your test.
So for the, like, let's say the review with something like that, the inverse tangent.
I would make sure that it was on your index card because it's probably going to show up on the test.
Okay, so it wouldn't change the, like.
I wouldn't put
inverse-
this right.
Okay.
Yes. So that was good question. That's actually very important. So when I write my test, I'm going to give you a practice test, which you're going to go through and do. And as remember I said before, I changed one little number and made it a lot harder. I won't do that again. But the test will be very similar rules. So if I'm going to use the inverse of sine on the actual practice test, you're probably going to need the inverse of sine on the actual test. Okay, so just keep that in mind for your index card. Couple things, especially for this and when we're going through some of the other stuff, the unit circle, if you don't know it, I would have some kind of similar thing on your index card or print it out so you can start to use it because it does come back a ton, especially when we're dealing with definite integrals because you're going to have to be plugging in pi and pi over 2 and those things, and knowing that unit circle is going to be important. I wouldn't try to write down the entire unit circle in your next card, but if you can look at just the first quadrant of it, like the pi over 6, pi over 4, pi over 3, and you know how to take that and make the rest of it, like being able to just do it out quickly, that will be helpful to you because those will come up into play. So, but yeah, I'm not going to make you try to memorize all this because you're not. And it's like, I honestly don't remember these. I just look them up. So, all right. So we've got this. Now let's do our problem. Let's see how crazy this problem comes out to look. All right. So we've got the arctangent of x. So I'm going to put the x in front, make it a little nicer to look at. Minus the integral of, actually, I should go down a little bit. And if you do arctangent instead of tan negative 1, it's fine. If you want to write arctangent, it's simpler to write the tan negative 1. Then we have v. There's 1 over 1 plus x squared dx. All right. So we've got the first part's done, and we still got the integral of a product, right? Okay. Which means we might have to do integration by parts. But think back to that trick problem that I gave you earlier. What do we always want to look for first? Well, look for simple solution first, including u substitution. U substitution is big. Now, if I made u 1 plus x squared, the derivative of that is 2x. And I have an x hanging out there. So this is a great example of using u substitution for it. So if I make m 1 plus x squared, dm is 2x dx. So I can bring over the 2, so it's 1/2 dm equals x dx. And that's going to take care of that and that. So now I'm just doing the integral of, I can pull out the 1/2 in front. So it's 1 over u du, which is ln of u, correct? Where did I lose you? I see the head shaking. All right, so you got to here? So looking at this, you almost have to, start to notice things when you're looking. And I've done it for long enough that I can notice things really quickly. You guys haven't. That's where the practice comes from. That's where just literally doing some practice problems, stuff like that. If you don't really remember U substitution, go back to section, I think it's 5.5 or something like that. We end in chapter 5, where they have the U substitution. Just try some of those. Start to notice patterns that show up. So in this one, you don't really want to do square root problems if you got something inside. You don't want to do division problems if you can get away with it. So we're going to look at division problems later on, partial fractions, and you're going to want to avoid division problems at all costs when we start to look at that method. Because if you think this one sucks, that one's way worse. So you really want to try to avoid that as much as possible. And one of the nice ways we can do that is with U substitution. So if you look quickly here, U substitution takes a derivative. What's the derivative of this? 2x. Okay. I don't necessarily have a 2x, but I do have an x that I need to get rid of. So that's good. Let's try. Worst case, it doesn't work and I try something else. And that's going to happen sometimes. Sometimes you're going to look and it's like, oh, this might work. And then you're going to go down and like, nope, it doesn't work. Cross it off, try something else. That happens. In this case, it does. So I didn't want to use u because I used u up here. So m is 1 plus x squared. So that's that. So now I do the derivative. That's what your substitution is. I do the derivative. So dm, oh, I didn't use a u down here. Bad convention. dm's. So dm is 2x dx. Now, I don't have a 2. So I've got to get rid of the 2 by bringing it over. And that's fine. You can bring over constants easily. Or coefficients, not a problem. You don't want to bring over variables unless you're brave and you really want to try something crazy. So the x has got to stay there, but I have the x, so I can get rid of it. So that's where I got this. So we good to there? Yeah. All right. So now we're going to plug that stuff back in and clean it up. So the 1/2, any coefficient I can pull out. Do that, because that's going to make my life a little bit easier. One less thing I have to worry about. That should be m. So 1 over m, that's just ln. So that's ln of m. Okay? And now I can go back and solve the rest of my problem. So I have my x arctangent of x minus, now this ends up being 1/2 ln of 1 plus x squared plus c. So we have this right when we do our notes later on. Then we change these back to m's. One half there.
You pull 1/2 out. So you don't look at 1/2.
Yeah. It's like you could do it. It doesn't make a difference. A coefficient doesn't really change the integral. You can still do the integral and just put the coefficient in front of it anyway. Sometimes it's nice to pull it out because it's one less thing you have to think about. But in this problem, I didn't want you to have to think about 1 over 2m because that might confuse you and not recognize that it's ln. For having the 1/2 out and just looking at the 1 over m, that should click. So. Or like in the last problem, when I pulled out the negative sign and made it so that it looked the same instead of having the negative sign in there. Little things like that can help, but it's not always necessarily necessary. All right. Let's give you one to try. Yeah, I did. It's right there.
Well, like for the definition.
Oh, no, I did. Oh, actually, no, you're right. It was a definite integral. I totally forgot that. Good catch. I didn't do that. I didn't need the plus c this time. The one time I remembered the plus C tonight. All right, we were doing this one. This was a definite interval, sorry, from 0 to 1, right? So we're doing this from 0 to 1. All right, let's plug in some numbers. So I have 1 times the arctangent of 1 minus 1/2 ln of 2 minus 0 minus 0, because ln of 1 is 0. So I don't have to worry about that part. So the arctangent of 1 is pi over 4 minus 1/2 ln of 2. There you go. If you tried to plug that into Desmos at the beginning, it would give it to you as a decimal. So, yeah, because of the arctangent. And the ln of 2, it wouldn't have told you that the ln of 2 was doing just decimal. It'll change decimals to fractions, but it won't give it to you in the exact thing with like ln and those type of things. This is where your unit circle really comes into handy. Knowing that the arctangent of 1, so remember arctangent is giving you the answer you want, the angle. So tangent of 45 degrees is 1, which is pi over 4. So that's where that unit circle is really going to help. 99% of the problems that you're going to see that has arctangents or sines and cosines and those type of things in it will give you ones that are on the unit circle, so you come up with an actual exact answer instead of having it be an estimate. So just keep that in mind. That's why I said that unit circle can really come into handy. All right. Now let me find you a problem to do. All right. This one. Everybody got the problem now? Okay, because I'm about to stop sharing this for a second. This way I can do it and you don't have to see what I'm doing. So inverse trig is the above algebra. Algebra is above trig. One time. Remember that was a mistake we made, the thing with the pi. We didn't pull the number out, it's one over it, so it's 1/10. And going from side to cosine, going backwards, you're going to the negative version. Oh no, that 10x is part of the side.
Oh,
Yeah.
That's good. Yep, that's actually good. So we got that part right and that part right. So actually is. Oh, let me make sure. I'm almost sure it's plus. Yeah, it's a plus. There's a couple extra signs in there because remember you're subtracting and then there's the negative thing. So I do, but other than that. When you pull out, when you do the process, you need something that. You end up having to do a substitution. So pull that out to 10. So that's, other than that, and this piece here, we should put through that. So it should be cosine. And negative cosine.
This is a little
Sine is after up. Or trig is after up. Inverse trig is before, not trig. Reverse.
for
So that's, so the mistake. No, actually, the only mistake, yeah, the mistake is that here actually, because we have to do something with that 10x, which almost everybody's missing. I'm going to show you in a second. It's just like that 1/2 that I did when you pull, when you have with that 1/2, that piece you have to pull out and get the 10x. Yes, Ocean University. Reverse. Yeah.
Just know that take this out.
Just right up.
Here, put it
Huh?
out, and multiply
No,
it
it's because you did,
times-
you have to reverse it and every, what you did there was right, but it's not the right direction. That's fine. That's.
No,
Which is
I
where
do
that-
also like.
So, yeah, you can't pull the 10 out from each side. Otherwise, you just pull 10.
And then
So yeah, it's just the number inside. Yeah, the only thing you're missing is the 10, that is that 10x. Okay. All right, so almost universally, everybody missed the 10x. Okay, which is fine. Well, not totally fine, but it's a mistake we will fix. All right, so 2 things. That's the answer, by the way. I'll explain why in a second. 2 things. First, remember I'll go back to it, don't worry. Remember this. So this is one of those things where you guys get stuck with exactly what we did before. So in the last problem, we had arctangent, and that was u. And I made my 1dx my dv. And then this problem, you go, oh, sine, that's u. And I put my x over here. Problem is that sine and arctangent are 2 different types of things. Arctangent's an inverse trig function, which is before algebraic. Sine is a trig function, which is after algebraic. So your x should have been your u. Your sine should have been your dv. Okay, that's mistake 1 that a bunch of people made. And that's why I said we did a problem like that actually earlier in class. So it's like, I know I said that, but it was one of those things like it was directly related to the problem you did right before it. You basically followed the same process. And you have to always go back and look at that mnemonic to make sure you're picking the right thing. Because what started happening was once you did that, is now you have x squared times the trig function. So your integral is actually getting harder and not easier. So then you kind of get stuck. The second thing is actually a bigger thing that you have to pay attention to, and that's when you're doing the integral over here. So let's just look at the integral of sine of 10x dx. Okay. First off, that's not sine times 10x, it's sine of 10x. In a situation like this, I have to do u substitution. So I'm going to make my u 10x, which means my du is 10 dx, which means I need to bring out my 10 because I don't have a 10 here to get rid of. Okay, so this problem becomes the integral of 1 over 10, which I can pull out, sine of u du, which ends up being negative cosine of u. So it ends up being negative 1/10 cosine of 10x. So you can start to do something which we call implied u substitution, because you really don't want to have to do this every single time you're doing a simple number. Like those coefficients are things that are going to show up a lot in the problems. And you don't want to have to necessarily do this step, all this work, every single problem. Okay? It becomes quite annoying. So what you can do is the number that's inside that coefficient basically becomes a fraction in front of it. So if this was 5, it'd be 1/5. If it was pi, it'd be 1 pi. If it was 100, it'd be 1/100. Whatever number is in front of there that basically is causing me trouble becomes a fraction in front. Because we would do the exact same thing every single time. The x is going to disappear. The number is going to show up there, and I'm going to pull it over. And it's going to become a fraction version. Okay? So you can do this. But once you start to notice that pattern, just imply. Okay? Just pull out the 1/10. And that's kind of what I did here. I just pulled out the 1/10. I didn't go through and do actually out all those extra steps. So this part, most people had right, except they didn't have the negative 1/10. They had x cosine 10x. They just didn't have the negative 1/10 in front. The other thing you got to remember is going from the integral from sine, you're going backwards. So the integral of sine goes to the bottom of that list, which is negative cosine, not positive cosine. Okay, so sines become an issue when you're looking at that rotation. Another thing that you might want to put down on your index card is just that quick for rotation for sine, cosine, negative cosine, so that you know which direction you're going when you're doing the derivative or the integration, because you're going to do both. And making sure you go the right direction can make a difference in terms of signs. And that can make a big difference in terms of your final answer, depending on what we're doing. Now I have to do the integral of this. I can pull out this 1/10 ahead of time. So this piece right here, this part right here, is actually no different than saying plus 1/10 integral of cosine 10x, which then goes back to that. Because again, I'm going to have another 1/10 pulled out. 1/10 times 1/10 is 1/100th. And the cosine becomes sine and stays positive. It's just going to take practice. All right. I'm going to end it there. My suggestion is I would definitely do some problems in section 7.1 before Thursday. Even just do like a handful of them. Go through, pick ones that you think you're going to screw up on, and try those. If you want the answer sheets to it, tell me and I'll send you the answer guide for all the questions. The only thing I ask, and actually because depending on which book you bought, you're supposed to get the 9th edition. It's fine if you don't, because it's exactly the same thing, just some of the problems changed. So you just have to tell me which edition of the book you have, if it's the 8th edition or the 9th edition. So I'll give you the right answer guide. So just keep that in mind when you tell me. So if you tell me you want it, no problem. Just tell me which edition you have and I'll send you the right one for it. So, all right. If you're doing the online one, I think it's actually 9E. I believe that one automatically updated, but if you have the actual book, you might have 8, which, like I said, nothing's changed. So I'm not going to make you go out and buy another book. So, all right. Any questions, just email me and I will see you on Thursday.
That sounds good.
All right.
Yeah, bro, I'm not.